In the last video, we were talking about the impact of fluid pressure on things like effective stress and total stress, and how the total downward force, which we called the total stress, was balanced by two things pushing back up, right? The fluid pressure and this thing called effective stress, which is basically how hard each grain is pushing against its surrounding grains. And the downward stress is equal to the upward stress, so that the rocks don't move around or the sediments don't move around. And you might wonder how you could, why do we calculate that? Why does it matter? Well, it matters because of this term right here, because of fluid pressure. If you were to remove fluid from an aquifer, particularly from a confined aquifer, then as the fluid pressure goes down, the total stress pushing down is the same. The two things pushing up are constant, right? But then if you remove the fluid pressure, if you reduce this, you have to increase the effective stress to compensate. So we can write it like this. Total stress, Ts, is equal to fluid pressure, Fp, plus effective stress, Es. So this is a constant. The downward force is constant. So then if you reduce the fluid pressure, you have to increase the effective stress, so that when you add this to this, they equal this term over here. All right, so why does that matter? Well, remember that there are two kinds of aquifers, right? There's the unconfined aquifer, where water is free when it rains to just soak into the ground until it hits the water table. And the more water that falls, the more the water table rises, right? Just like water in a glass. This is unconfined. It's unconfined aquifer. However, a confined aquifer is quite different, right? Because it is confined by geology such that you have a relatively impermeable layer above and below. So this would be the confined aquifer. And these would be something like a shale layer or some other kind of relatively low permeability rock that we refer to as an aquiclude, actually an aquitard, mostly here and here. So when it rains, the water soaks in, but the water will form an unconfined aquifer here that just represents this portion. Basically, the bottom of the unconfined aquifer is the shale layer. So you have an unconfined aquifer here, and the water has a very, very difficult time soaking through this shale and impacting the confined aquifer. This confined aquifer is kind of like, you can think of it like almost like a hose at the bottom of a pool. There's water around it, but the water in the pool is unable to sort of talk to or influence the water in the hose. The water in the confined aquifer is more or less immune from the water levels out here. Okay, so let's just think about this confined aquifer for a minute. So we have the weight of the overlying rocks and water and everything pushing down on the shale. And what's pushing back up? Well, you've got the fluid pressure in the confined aquifer, and then you've got the grains, the effective stress, the grains pushing against each other in the confined aquifer. And those two things have to equal each other. So what happens if you, let me draw this, start over here and make a bigger map. What happens if we have a confined aquifer here in between two shales? And we drill a couple of wells down in there. And what do we find? We find, here's a well. Hope that shows up. Yeah, that shows up. And here's a well. So we'll call this well A and well B. And the water rises in well A to, let's say, right here. And the water rises, let's say, in well B to over here. Okay, something like that. So what that tells us is that there's enough water pressure in this confined aquifer so that when we puncture it, when we drill a well that goes through the shale layer, the water rises up in the well to this point here, well above the shale layer. And the same thing happens over here, right? Well, what happens if instead of just putting that well in and seeing where the water goes, we actually pump the water out? And we have to put a capital Q there, because Q, remember, is for volumetric flow. So that just means we're taking out some volume of water per second. We're pumping it out. What's that going to do? Well, what it's going to do essentially is it's going to reduce the water pressure in the confined aquifer, the same way that if you take a water balloon and you put a pin in it, right, and the water starts spraying out, the water balloon begins to get smaller and smaller and smaller because it's losing water. Well, so what's happening there? If we're taking water out, as we pump this water out, we are reducing the fluid pressure in this confined aquifer. There's less water in there to do the work. And so as the fluid pressure goes down, the effective stress has to increase. Has to increase by the same amount that the fluid pressure goes down. And as a result, what happens is the grains, which we can imagine looking kind of like this, if we zoomed in on them, right? They are squeezed together under a tighter and tighter configuration. So they may start out looking like that, but they may end up looking like that. So the pore space, which is this space here, in between the grains, has been reduced because the grains have been crushed in on themselves due to an increase in effective stress. And the reason that's happened is that the water, remember, that used to be filling those pores was helping to hold up the roof, was helping to support the weight of this shale and everything above it. But when the water's gone and the fluid isn't able to help carry the load, the grains contract into a smaller area. Excuse me. So what are the impacts of that? Well, if this is a solid rock, if this confined aquifer is like a solid, rigid sandstone, then not much happens. If it's a rigid, solid, strong, say sandstone or limestone or something like that, not a whole lot happens. But a lot of these confined aquifers are formed in areas where you don't have what are called lithified sediments. They're unlithified. And remember, lithification is the process of turning loose sediments into solid rock. And the way you lithify sediments, remember, is in large, you cement them together. Remember, we talked about this the other day. You have you have some grains of sand like this, and if you pick them up, they just fall apart. But if water flows through, over time, little crystals will begin to form on the edges of these things, crystals that are forming from the minerals that were dissolved in the groundwater. And as those crystals grow, they grow from the side of one grain into another grain, and they act like little bits of glue, and they end up gluing the sediments together and forming them into a solid rock. So if you have a lithified solid rock, you pump the water out, not a lot happens. However, if you've got an unlithified sediment like loose sand or loose silt or loose clay, then by reducing when you reduce the fluid pressure, then these grains are free to shift around a lot. And as a result, what you end up with is compaction. The grains get shifted into a more compact configuration, and as a result, what happens? The confined aquifer becomes thinner. Becomes thinner vertically. Becomes thinner vertically. And that may not sound like, I mean, who cares, right? Well, it turns out that when you have really, really compressible materials, like clays and silts, and you have really thick deposits, as you can get in some parts of the world, and you pump a lot of the fluid out, which has been done, you get a lot of compaction. And the consequences of that are pretty remarkable. And you'll be reading about this you're going to read the USGS reading titled Subsidence, which will be posted if it's not already to Moodle. Because what subsidence means is the land surface actually subsides as the underlying rocks become thinner and thinner. And we can actually calculate the amount of subsidence that we might expect to get. And the thing that we need to know is basically the most important thing to know is the compressibility of the sediment. Compressibility of the sediment or of the material that makes up the aquifer. The confined aquifer. You really don't get this kind of effect in an unconfined aquifer because the water is just sort of filling in randomly wherever there's an open space, but the water's not bearing any of the weight of the overlying rock. It's only because the water is trapped in the confined aquifer that it bears the overlying weight. So, okay, here are some compressibilities. Compressibility is given as alpha, and so we can list compressibilities of different materials. By far the most compressible is, and these have funny units of meters squared per Newton. The average value for the compressibility of clay would be 10 to the minus 7. For sand, it would be 10 to the minus 8. For gravel, it's 10 to the minus 9. For solid rock, it's 10 to the minus 10. And for water, it's 4.4 times 10 to the minus 10, which is interesting, right? You can see that water is almost is actually more incompressible than solid rock. Water is a very highly incompressible fluid. So let's do a calculation then. Let's say, first of all, the equation. Okay, so what's the equation we can use to calculate these kinds of things? So the calculation is, or the equation is B1, I'll explain what these mean in a minute, equals B naught e to the alpha, which is the compressibility, times the density of water times gravity times H1 minus H naught, or H sub 0. Is that visible? That's visible. Okay, so what do these all mean? So B1 is the thickness of the aquifer after pumping the water out. B naught is the thickness of the aquifer before pumping. This should be after pumping. Before pumping. E is just the natural log function. Alpha is the compressibility, which we already defined. Rho W is the density of water, which is 1,000 kilograms per cubic meter. G is gravity, which is 9.8 meters per second squared. Sorry, that's supposed to be H1 there. H1 is the hydraulic head after pumping, and H naught is the hydraulic head before pumping. Okay, so let's see what all that means. Let's do a little calculation here. Let's say that we have a hold on. All right, it's still working. Okay, let's say that we have a 100 meter thick confined aquifer, and its initial hydraulic head. The hydraulic head is at 150 meters. And we're going to pump it down before pumping. And we're going to pump water out until the hydraulic head falls to 140 meters. Remember, the hydraulic head is essentially just an elevation. Yeah. All right. Let's see, where are we? All right. So then the question is, how much subsidence? How much subsidence occurs? All right. Well, the one thing I haven't told you is what is this confined aquifer made of? So let's do it for two cases. Let's say A, it's a sand, unconsolidated sand, and B, it's a clay. Now, clay wouldn't make a very good confined aquifer at all, but this sort of illustrates the point. So so let's see, what's the equation? So the equation would be the new thickness, B1 equals B naught e to the alpha density of water, gravity, times H1 minus H naught. So B1 equals B naught, which is 100 meters, times e to the, and then for sand, this would be case A. Sand, the alpha is, what did we say the alpha is for sand? It's 10 to the minus 8 times the density of water, which is 1,000, times gravity, which is 9.8, times the difference in hydraulic head, which is 10 meters. And when you crunch the numbers with, let's see, let me double check that. I think I might have done it with different numbers. Let's check here. Hold on. So what did I use? I used 10 to the minus 1, 2, 3, 4, 5, 6. I used 10 to the minus, okay, hold on. 6. Okay, so we're using 10 to the minus 8 for sand, and so B1 is at 10 to the minus 8, it's 99.9 meters thick. Let's see if this is still. So the aquifer dropped 1/10 of a meter in thickness. So B naught minus B1 is 100 meters minus 99.9 meters. So the amount of subsidence was 0.1 meters, not very much at all, right? So what is that, 10 centimeters, which is about 4 inches. It's not trivial, but it's not a ton. If we were to do the same thing with clay, we would do this entire calculation the same, except we would put 10 to the minus 7 in here instead, times 1,000 times 9.8 times 10 meters. Sorry, this would be negative 10 meters times negative 10 meters. And when we calculate it, we get a new thickness of, I'll just double check my work here. .0. I did that right. .0, which is 100 minus 99 is 1 meter. So the land surface dropped 3 full feet, 1 meter, by pumping out 10 feet worth of hydraulic head of water out of this aquifer. That's not trivial. It doesn't maybe not sound like much, but these things add up. And there are some really classic examples of subsidence, which you will see when you read this. It really is pretty fascinating and scary. This U.S. Geological Survey blurb on subsidence. So some classic locations where this has occurred. And by the way, it doesn't have to be water that you pump out. It can be oil. So you just have to remove a fluid from a confined aquifer. So you can get removal of oil or water can cause subsidence. And so things like one of the classic examples in the U.S. is the San Joaquin Valley in California, where they've been mining groundwater for irrigation. And this might be a little bit outdated, but it's pretty close. 8.5 meters of subsidence. So if you multiply that by 3, that's about 27 feet. That's like a 2 or 3 story building. And you will see photos of this, pretty remarkable photos in that little USGS thing. In Houston, Texas, we're talking about close to 3 meters. And that's a lot of oil being mined. Mexico City, which was built on an old lake bed. Mexico City, about 8 meters. I've not been there in person, but supposedly there are these dramatic examples of sunken churches and all sorts of things. And even Long Beach, California, where oil was mined or withdrawn, 9 meters. 9 meters of subsidence. It's pretty remarkable. Then you might say, okay, well, what's the big deal? You take the water out, you get this subsidence, then you can just pump the water back in. Well, it turns out that there's that once the water is withdrawn, and subsidence has occurred, it is next to impossible to recover the original thickness and to prop the land back up. This is largely irreversible. So it's a big problem, right? It's a big problem for flooding, for cracking, because if you're lower in elevation, you're more likely to be flooded, for cracking of foundations of buildings, highways, wells, all sorts of problems, and it's still going on today. So anyway, we'll come back and talk more about this soon.